Hello friends. So today we are going to solve the questions which were asked in the year 1984, 1982, 1981, and the last one is from the year 1983. So there will be a total of 4 questions. So in the first one, which was asked in the year 1983, and it says that a conducting circular loop of radius r carries a constant current I. It is placed in a uniform magnetic field B0 such that B0 is perpendicular to the plane of the loop. The magnetic force acting on the loop is. In this case, we are given a circular loop of radius r which carries a current I and placed in a uniform magnetic field, and this magnetic field is perpendicular to the plane of the loop. Okay. So if you consider that there is a small element dl, so let us consider a small element dl on the loop. Therefore, the force acting on this small element dl, so therefore magnetic force acting on dl, let us suppose that is given as df, then this df will be equal to current, and we have dl cross product with b. Okay. And here the now in this case we have a loop, and that loop is of radius r carrying a current I. Okay. So we can say for a circular loop of radius r carrying a constant current I, placed in a uniform magnetic field B0 and placed in a uniform magnetic field B0, and this B0 is perpendicular to plane of the loop. From this entire description, we can draw two important conclusions, and the first conclusion is that the small length dl is tangential to the loop. And second is that magnetic field B0 is perpendicular to the plane of the loop. B0 is perpendicular to plane of the loop. Therefore, we can write that the force dF will be equal to I dl cross product B0, and the magnitude of, we can write this as I B naught dl, and this df force, the direction rather, you can say the magnitude is equal to I B naught dl, and direction of df is radially outward, is radially outward at every point on the loop, at every point. So therefore this small force df is symmetrically distributed around the circular loop. So you can say the force on each small element is symmetrically distributed around the circular loop, around the circular loop. So therefore we can say the forces cancelled out in all direction. The forces cancels out in all directions, which gives us that net force is equal to 0. So here the option number C is the correct option. Option C is correct. In this case, if we are supposed to find out the torque will not be equal to 0. Net force is 0, but loop does experience a torque. Experience a torque, and that is given as torque is equal to M and B, where M is the magnetic dipole moment, and it is given as IA and a unit vector N, which is perpendicular to the area, gives us the direction of the area in which it is facing. It is our magnetic dipole moment. Magnetic dipole moment. Now we solve the next question. It was asked in the year 1981, and in this question it says that the potential difference of 600 volt is applied across the plates of a parallel plate condenser. The separation between the plates is 3 mm, and electron projected vertically parallel to the plates with the velocity 2 into 10⁶ meter per second moves undeflected between the plates. Find the magnitude and the direction of the magnetic field in the region between the condenser plates. Neglect the edge effects. The charge on electron is given as 1.6 into 10⁻⁻19 coulomb. In this case, we have to keep in mind the important thing is given that the electron moves undeflected between the plates. So you have to keep in mind that electron moves undeflected. Between the plates. So we are given this figure, and we have electron which is moving a parallel. So this is the electron hour, and positive and negative, and it has a potential difference of 600 between them. So obviously, if it is moving undeflected, then we can draw one important conclusion, that the magnitude of the electric force and magnetic force must be equal in magnitude but opposite in direction. So you can say the electric force is equal to magnetic force but opposite in direction. Because under this condition only, the electron will be moving undeflected. That means it will be going straight and following this path. So first of all, let's find out what will be the electric field between the plates. Electric field between the plates, and we can write this as E is equal to V upon D. We substitute the value, it is 600, distance is about 3 millimeter, so this comes 3 into minus 3, will be about 2 into 10 raised to the power 5 volt per meter. So this is the electric field. Now we can find out the force because of electric and magnetic. We can say electric force and magnetic fields rather. So yeah. Electric and magnetic forces. So first of all, let's write the formula of electric force. Electric force, if given as Fe, will equal to charge on electron and the magnitude of E, and we have the magnetic force. Let us call that Fb, which will be equal to charge, velocity and value of the magnetic field, and the magnitude will be equal for undeflected electron. So we can say, since electron moves undeflected, the forces are equal. So which means force due to electric field will be equal to force because of the magnetic field, and this gives us our electric is equal to EVB. Here electron charge cancels out, and we can write that we need to find out value of magnetic field. So our magnetic field will be equal to the electric field divided by velocity V, and we substitute the value, we get 2 into 10 raised to the power minus 3, 2 into 10 raised to the power 5 divided by velocity is also given as 2 into 10 raised to the power 6. So it comes as 0.1 Tesla. And yeah, we found the magnitude, but he also supposed to find out the direction. And for direction, of magnetic field, now the electric field will be from our positive to negative direction. So electric field will be in this direction. You can say electric field is directed from positive plate to negative plate, and let us call this as a positive x-axis. Okay, so this is our x-axis and this is our y-axis. Positive x-axis. Now electron moves parallel to plates, or we can say positive y-axis. So therefore, the magnetic force on electron must be opposite to the electric force. For electron to remain undeflected. So we can use right hand rule for V cross B, okay, because that is a cross product of velocity. The force is rather cross product of velocity. So you can say right hand rule for V cross B. So it means that our B will be directed into the plane of paper, that is negative z direction. We can say that our B is directed into the plane, or we can say negative z axis. Or from here we can also say that it will be perpendicular to plane. And this completes our second question. Now we come to the third question, and which states that a particle of mass 1 into 10 to the power minus 26 kg and charge plus 1.6 into 10 to the power minus 19 coulomb, traveling the velocity of 1.28 into 10 to the power 6 meter second in the x direction, enters a region in which a uniform electric field E and a uniform magnetic field of induction B are present, such that the electric field in x direction is equal to electric field in y direction and the both values 0, whereas electric field in z direction is given as minus 102.4 kilovolt per meter, and magnetic field in x direction is equal to magnetic field in z direction, magnitude is 0, whereas our B of y is given as 8 into 10 to the power minus 2 Tesla. The particle entered this region at the origin at time t is equal to 0. Determine the location x, y and z coordinates of the particle at a time t 5 into 10 to the power minus 6 seconds. If the electric field is switched off at this instant with the magnetic field still present, what will be the position of particle at t is equal to 7.45 into 10 to the power minus 6 second. So in this case, we are given that there are two fields, electric field as well as magnetic field, and they are only present, electric field is only present in z direction and magnetic field is only present in y direction, and the particle enter at 0 at t is equal to 0 time. So we have to find out the location x, y and z coordinate of the particle at time t is equal to 5 into 10 to the power minus 6, and after this time the electric field is switched off and magnetic field is still present, then we have to find the position of particle after this time. Okay. So in this case, first of all, we can say draw the basic representation in which all the fields are present. So we are given that, suppose this is our x direction, this is our z direction, and we are having a y which will be something like, let us suppose, and we have our magnetic field only present in y direction. So this will be our magnetic field, and electric field is only present in z direction. And it enters the origin at time t is equal to 0. Okay. So let's understand all the forces acting on the charge whose value is given as plus 1.6, and in this case there will be both forces, electric field as well as magnetic field, acting on the charge. Okay. So we can say that force on the charged particle let us call that a force F, which will be a combination of electric as well as magnetic force. So we can see Q, this comes as E plus V cross B, and we can find out the electric field is only present in, you can say, in z direction. So let us find out the force, this particular value. So we can say electric and magnetic forces, First of all, let's find out our electric force. Our Fe, which will be equal to, and this is only in z direction, electric z direction, and we can write this, our electric force will be equal to charge electric field in z direction. We substitute the value 1.6 into 10 to the power minus 19 minus, this is given as 102.4 into 10 to the power 3. So we get our electric force will be 1.6384 into 10 to the power minus 14 Newton. And this force will be in the downward direction because of this negative sign. Okay. You can say this force is directed downwards. Which is our negative z direction. Now we can find out a magnetic force. Magnetic force, that is our FB, and this is our Q Vx, and we have this as By, and the velocity is given in the positive x direction. Okay, so the particle is moving in this direction with the velocity v. So we substitute the value, we get our FB is equal to 1.6 into 10 to the power minus 19. Velocity is given as 1.28 into 10 to the power 6, and magnetic field in y direction, it is given as 8 into 10 to the power minus 2. So this gives us that our magnetic field FB will be equal to 1.6384 into 10 to the power minus 14 Newton. Now we can find out the direction of this magnetic field. And for direction, we can use a right hand rule, and which gives us that our Vx, it is along positive x direction, and we have our magnetic field is in positive y direction. So this V cross B will be in positive z direction, or we can say upward. So if it is getting upward, we can easily modify the figure. Let me draw it again. So we were having our, this is our positive x direction, this is z, and this is our y direction. The electron is traveling in this direction with the velocity v, and we have our magnetic field in y direction, and electric field is in z direction. So the net force on the electron, we can just draw it again. Suppose it is somewhere here and is moving in this direction with the velocity v, and at this particular point it will be having two forces. One is downward, negative z, another one is a positive z. Okay. So upward direction, we are going to have our magnetic field, and in the downward direction we are going to have our electric field. So it will be having a tendency to move in a straight line. And let us find out what will be the net force. Okay, obviously if we see from the, because the magnitude in the both the cases is same. It is 1.6 with a negative sign, and here we have a with a positive sign. So net force will be 0. So it will be traveling in straight line. Okay. So you can say the net force, let us suppose that is given as F, will be equal to Fe plus Fp, and if we substitute the values, or you can just write it 0 directly also, okay, because it will be coming as 0. So from here we can say that the net force is 0, so the particle experiences no acceleration. So this is important conclusion from here, that the charge experiences no acceleration. No acceleration in z direction, and continues to move with the uniform velocity Vx along x-axis, and continue to move with the uniform velocity Vx in positive x direction. Now let's find out what will be its position at time t1, which is given as 5 into 10 to the power minus 6. Position at t1, which is our 5 into 10 to the power minus 6 seconds. So as there is no acceleration, we can use simple displacement formula. We can say that the displacement in x direction let us call that as x1, is equal to Vx multiplied by t1, and this is 1.28 10 to the power 6 multiplied by time is our 5 into 10 to the power minus 6. So we get our x1 is 6.4 meters. Okay. So we can write that, let me draw it here. This is our x direction, this is our z, and this is our y direction, and you can say that the particle is somewhere here. This is our x1, and this x1 distance is 6.4 meter from the origin, so the coordinate will be 6.4 0, 0. So we can say at t1, so this is its position at t1. At t1, the particle's coordinate are, let us call them x1, y1, z1, and that will be our 6.4 0, 0. Now it says that after time t1 the electric field switched off and now only the magnetic field is present. Motion after t1, and now the electric field is switched off. So from here you can say that the particle only moves under the influence of magnetic field. The particle only moves under the influence of magnetic field. Therefore, it will start to move in a circular path or circular motion, because the magnetic field is perpendicular and acting in the upward direction. Okay, so this is the motion of the particle, and magnetic field is perpendicular to the velocity. Our magnetic field is perpendicular to the velocity. Okay, so it will try to move in our xz plane. You can say circular motion in xy plane. Circular motion in xz plane, not xy. Xz plane. And because of the circular plane, we can easily write the equation which gives us that radius of the circular motion or radius of the circle. You can say that radius of circular motion, if given as r, then this r will be equal to mvx divided by q multiplied by by. And this equation is quite simple because of the centripetal force that will be our, and that will be balanced by our you can say the magnetic force. So we substitute the value, we get this as radius r will be equal to 10 raised to power minus 26, and we have 1.28 into 10 raised to power 6 divided by 1.6 into 10 raised to power minus 19, and we have this as 8 into 10 raised to power minus 2, and this will be equal to our 1 meters. So we can just draw an approximate diagram for this also, and we have x-axis, z-axis, and this is our y-axis. Electric field, magnetic field, and we have the particle traveling in this direction. And let us suppose at this particular point, let us call this as point P1, the electric field switched off. So we get this as x1, and then it will try, and we can also write that here will be our magnetic force and our electric force, and here it will try to move in something like this path. Okay. And this is the, you can say, path of particle in xz plane. Path of particle in xz plane. Suppose we have center of this particle, and this is center as O, and we have radius r, and P2 is our position at the respective time, or its coordinate we are supposed to find out. So obviously it will be x2 and z2 only. Y2 will be 0 because the plane is our xz. And if this angle is theta, so we can say this height will be our r cos of theta, and let us suppose this is given as z2. So we can write this will be given as r sine of theta. So the total distance with respect to the origin, let us suppose that is given x2, which will equal to x1 plus r sine of theta, this distance. So this is our basic figure. Now we can just find out the various values which will be associated with it. We can say the angular displacement which we have said is our theta. We can write the angular displacement over the time delta t, which is given as t2 minus t1, and that will be our over the time delta t is equal to theta, and this theta we can write that our theta is equal to velocity in x direction delta t divided by r. Here our delta t is equal to t2 minus t1. Now we simply substitute the values. We can write our theta velocity is our 1.28 into 10 raised to power 6. Delta t is our t2 is our 7.45, and it is 5. We have this as 7.45 into 10 raised to the power minus 6 minus 5 into 10 raised to the power minus 6 and divided by radius, which comes as 1. So our theta comes approximately as 3.136 radians. And this is, we can say, can be approximately as pi. So it means the particle completes a half circular motion. Okay. So it will be completing a half circular motion, something up till here. You can say, therefore, thus the particle completes half circular motion. of circular motion. So now we can find out the final position at time t2. Final position at t2, which is our 7.45 into 10 to the power minus 6 seconds. And we just, you can say, wrote the formula in, so this is our x2 and this is our x1. So we are only interested in our x2. So we can say that x coordinate which will be given as x2 will be equal to our x1 plus r sine of theta. Theta we just found out is our pi, so sine pi is 0. So we get our x2 will be equal to x1, which is our 6.4 meters. And obviously the y coordinate will be 0 because it is in xz plane. So we find out the z coordinate. Z coordinate, which we wrote at z2, will be equal to r minus, and we have that as r cos of theta. Cos of theta, theta is pi, which comes, cos of theta is minus, you can say minus 1. So we can write our z is equal to r. This comes minus of minus 1, giving us r plus r, that is 2r, and this is about 2 meters. So therefore the coordinate at time t2, the final coordinates at t2 is our x2, y2, z2 will be our 6.4, 0 and 2. Now we come to the next question. It was asked in the year 1994, and it says that the particle of mass m, 1.6 into 10 to the minus 27 kg, charge 1.6 into 10 to the minus 90 coulomb, enters electric field in the region of uniform magnetic field of strength 1 Tesla along the direction shown in the figure. The speed of the particle is 10 to the 7 meter per second. So based on this, we have two questions. In the first case, it says that the magnetic field is directed along the inward normal to the plane of the paper. The particle leaves the region of the field at a point F. Find the distance EF at angle theta. And the second, it says that the direction of field along the outward normal to the plane of the paper. Find the time spent by the particle in the region of magnetic field after entering at E. So this particular figure is for, you can say, A part. It says that it enters at point E, magnetic field is into the paper, and it leaves from the point F. And we have to find out the distance EF, this distance, and we have to find out this angle theta. And the second part, it says the direction of magnetic field is reversed. Now it is coming out of the paper. And then we are going to find out time inside the magnetic field. So let us solve for part A. And let us redraw the figure. So we have a magnetic field at this border, it is given that we have a point F, and here we have a point E, and we are supposed to find out this. We have this point F, let me write it here, and point E, and the electron or charged particle enters in this direction, and as soon as it enters the magnetic field, it is going to follow a little bit of circular path and leave the point F in this direction. And angle theta, with the vertical. So this is angle theta. Theta angle is there. In this case, because it is like type of a part of a circle, so let us draw. This is a center, which is, let's suppose, given as C, and we join all these points. This is C, and we draw a perpendicular, and this point we call as a G. And the velocity vector will be somewhat tangential at this. So this will be direction velocity vector here, and similarly there will be tangential velocity vector in this direction. So this is our radius. Let us call here small r. So let me redraw this particular figure here. So this is our F, and this is point E, and we have a velocity vector which is in this direction at this point, and here we are also going to have a velocity vector which will obviously be tangential to this curved path, and we have center C, and this is our G, and here it is making angle of theta. Okay. So we can easily understand this angle will be over 45, and this angle will be also 45, and this will be over 90 degree. So we can write that our angle CFG, okay, we need to find out this angle, okay, and this angle will be equal to, because vertical opposite angle, this angle will be over theta, and we are going to have, this is a radius vector and this is a tangent, so this will be over 90 degree. So we can write this angle will be over 90 degree. So we can write that angle CFG will be equal to 90 minus theta, and from the figure we can also see that our CF is equal to CE, and each is equal to radius. Therefore angle CFG will be equal to angle CEG. Both will be equal, and we can also say that we can write this as angle CFG will be equal to 90 minus 45. This comes as 45 degree. CFG. So theta will be also equal to 45 degree. So this was quite simple, based only on the trigonometric condition, okay, because this was our tangent and this is our radius vector, so both are here 90 degree, and because of this property we can easily find out the value of the theta. Now let us try to understand for part A, what will the force be acting on the particle, and you can say forces on the particle. So the only force will be acting on the charged particle. Let us suppose that is given as F. So F will be equal to QVB sine of alpha. And here we assume that alpha is the angle between the velocity and magnetic field. Okay, normally we take theta, but theta is already given in the question. So we say alpha, which is angle between velocity and magnetic field, and that value will equal to 90 degree because they are perpendicular to each other. So we can write that our F, substituting all other values, this is 1.6 into 10 raised to power minus 19. Velocity is also given to us 10 raised to power 7, and sine 90 is our 1. So this comes as 1. Therefore we can write that our force will be equal to 1.6 into 10 raised to power minus 12 newtons. Okay. Now this will be acting perpendicular to velocity and providing the centripetal force required for the circular motion. We can say this force acts perpendicular to the velocity, providing centripetal force. Centripetal force required for circular motion. Required for circular motion. Now we can find out the acceleration. Acceleration of particle, if it is given as A, then we can write that this A will be equal to force divided by the mass, and force we just calculated is 1.6 into 10 to the power minus 12. So we can write our acceleration will be equal to 1.6 into 10 to the power minus 12, and mass is also given as 1.6 into 10 to the power minus of 27. So this gives us that acceleration will be equal to 10 to the power 15 meter square, meter sec per square. And this is nothing but a centripetal acceleration, we can also call it. This is centripetal acceleration. And we can easily find out now the radius of the circular path. Radius of circular motion. And from centripetal, we can say that our A will be equal to V square upon R, and we can say our R is equal to V square upon A. We substitute value, velocity is given at 10 to the power 7 whole square, acceleration we found out 10 to the power 15, so this comes as 10 to the power 14 divided by 10 to the power 15. So the radius is our 0.1 meter, or we can say the 10 centimeter. And now we can easily find out the distance EF, which we are supposed to find out finally. Distance EF, and basically the particle is now moving along an arc which is forming an angle, total angle of, we can say, 90-degree sector angle, and chord length is EF. So distance EF, which we can write that our EF is equal to 2r and cos of the 45, and cos of 45 is 1 by square root of 2. So we get our EF is equal to 2 into 0.1 into 1 upon square root of 2. So we get this EF is equal to 0.141 meters. And we are given case 2, the magnetic field is now outward. Case 2, we are given that magnetic field is outward. So we can just draw an approximate diagram for that also. We are given that we have magnetic field in outward direction and rest of the things will be same. So along this border the electron will be entering, and once again it will be moving in a circular path. And let us draw a, so this will be close to the circular path, and its center is given as C, and so once again we have the velocity vector, and please keep in mind now it will be traveling in the opposite direction as compared to the previous case. Okay, so let me redraw it again. So this is our circle, and we have in opposite direction now, in this direction. So we have this angle as 90, and this point is our F, this point is our E. Once again we can just draw the velocity vector. So this will be something like this. So velocity vector will be coming tangential to this point here, and here also it will be like a circular path, and this will be the circle out of the magnetic field like this. So we are going to have once again this angle will be of 45, and here also there will be angle of 45. And in this case, like I said, the magnetic field is outward, but the particle follows a circular path. Circular path, but in clockwise direction. In clockwise direction. And in this case, the particle is going to complete 3/4 of its of circle inside the field. You can say the particle completes 3/4 of the circle inside the field. Inside the field. So we can easily find out the time for full circular motion, and then we can make it a 3/4. Time for full circular motion and that will equal T is equal to 2 pi m divided by Q multiplied by B. We simply substitute the value. 2 pi mass is given as 1.6 10 to the power minus 27 divided by charge is given as 1.6 into 10 to the power minus 19. Magnetic field is 1 Tesla. So we get this time will be equal to 2 into 10 to the power minus 8 times pi. And let me solve it completely. And pi is our 3.4. So this comes as multiplied by 3.14, giving us that the time will be 6.28 into 10 to the power minus 8 seconds. So this is the time for complete, you can say complete circular motion, complete circle. And we know to 3/4. So we can say time for 3/4, we will put 3/4 multiplied by T. And we substitute the value, we get 3/4 multiplied by 6.28 10 to the power minus 8. So this gives us time for 3/4 will be coming as 4.71 into 10 to the power minus 8 seconds. So this completes all the questions. So we solved, you can say, 4 questions, year 1984, 82, 81 and 83. So this completes all the questions. Thank you.